In example number 6 here, we're actually going to go ahead and take a look at how I might be able to evaluate the integral of a complicated looking function here without actually really using any integration properties. Instead here, what I'm going to note is that sometimes for very specific functions, I can see that there are going to be some nice geometric areas that I can take advantage of. Let's take a moment here to think first about what exactly we're working with and try to see where exactly these special area formulas may come in. So I'm first going to go ahead and think about the function here that I'm integrating. So I'll write that down. We first think about y equals 1 plus the square root of 9 minus x squared. Now, I should be able to note here that if we had y equals just the square root of 9 minus x squared, like if we just pretended that the 1 wasn't in there for the moment, then of course we could rewrite this equation many times over very, very easily. We could say that I could square both sides and end up with y squared is equal to 9 minus x squared. But of course then I could rewrite this again by adding the x squared over to the other side. I could get x squared plus y squared is equal to 9. And actually, do you recognize what this would be the equation of? Well, this would be the equation of a circle with a radius of 3. So the only thing that's really different here is that I should note that I wasn't given exactly this formula here. I was given this modification. Notice that when I came back, I square rooted both sides. If I kind of reverse the order here, if I square root both sides, I should have had a plus or a minus. But I don't have a plus or minus here. I only grabbed the positive portion. So I'm kind of only going to have 1/2 of a circle here, the top half, where the y values are positive. And then with this plus 1 on there, I can see that that circle that I would have had essentially got shifted up by 1 unit from where it would have normally where it would have normally fell. So let's take a look at what this would actually look like here. Let's suppose that I try to sketch this out, okay? A rough picture of what this might possibly look like. So if I was going to go ahead and sketch this out, I would see that I would start by kind of imagining a circle with a radius of 3, maybe something that kind of looks like this, but again, only the top half. And then again, I have to imagine that I'm going to bump this up by 1 unit because of my plus 1. So if I was to put all of that together, I could see that I would maybe have a circle that goes something kind of like this. Okay, now again, not perfectly drawn to scale here, but this is roughly what I have. I should note that if it's a circle with radius 3, then I should be moving over from -3 to +3. And wherever the center is, it should be 3 up to the edge. But notice my center here is now going to be at 1 since I bumped everything up 1 unit. So my top here is going to be at the value of 4. Well, what I can do now is recognize that I'm just interested in finding the area from from -3 to 0. I'm interested in finding all of the area here in red, all of this space. This is what I'm interested in finding. This is my red integral. Now, to compute this, I can note a couple quick things. First off, since I was dealing with the area of the equation of a circle, I might be able to use the area of a circle formula to try to at least find a portion of this area here. Take a look at how I might be able to quickly kind of divvy this up into 2 distinct regions. If I was to go here and draw kind of a nice horizontal line right across here at 1, I could see that this bottom portion here is actually just a nice little rectangle, and I could find that area no problem. I could also see that up here then, what I have is just a portion of a circle, technically a quarter of a circle, right? Not a full circle, just a quarter of it. And so maybe I could find this green area and this blue area, and I could add them together to make the red area. So let's actually try this. I'm going to go ahead and start with the easiest of these two areas, which would be the area for my rectangle. Now the area for my rectangle here, of course I can find that by just doing the length times the height. The length here seems to be just 3 units long, and the height appears to be 1. So the total area for this is going to just be 3. Now, if I wanted to find the area of my circle, I recognize I'm going to need to use the area formula for a circle, which would be pi r squared. But then, since I only want a quarter of the circle, I don't want the full area for the full circle, I'll just multiply this by a quarter. And I just need to know what the radius is for this circle. Oh, and we already said it was radius 3. So notice if I simplify this out, let's see, 3 squared is going to be 9. So I'm going to get 9/4 pi. That's the area. So now I can easily state what the total red area is. I can say, therefore, the integral from -3 to 0 of 1 plus the square root of 9 minus x squared is equal to, and I can just add together these two distinct areas. So I can say I'm going to take the area of my rectangle, I'm going to add on the area of my circle, and of course that's going to leave me with 3 plus 9 pi over 4. It's not really a cleaner answer than that. That's looking really, really good. And notice that this didn't require that I use really any calculus at all. And sometimes this is possible if I have nice, easy geometric shapes. And so I want to make sure that, that I'm on the lookout for nice geometric shapes. I want to see rectangles and triangles and quarter circles and half circles. I want to see those things within my pictures, because that might make it a lot easier to find the area without having to go through more complicated calculus routes.